Hello, in this video we would like to cover the nuclear power plant. By the end of this video, I will hope we all can learn the idea of these four things, including critical mass, moderator, fuel rods, and control rods. And also we will do this example question. Let me show you a basic idea of nuclear fission using this simulation. If you also want to try this simulation, you can go to the link I put down in the description below and you can go and download it. However, this will require you to use something called Java to run the program properly. And sometimes people may find it tricky if you're especially using MacBook. It may be difficult for you to run. So PHET, this organization is so nice that this year they have created a new way to use it, so you don't have to download it. So here I've got you another link again in the description below. You can then try to run this simulator online, so you don't have to download anything or install JavaScript, and it will be exactly the same as what I have here with different tab, but this would be a slightly slower in terms of the speed. So it's really up to you. I personally prefer using this because I've already installed Java. But if you really can't do it, then go to this link to use it. Okay, so first of all, what happened in one nuclear fission is usually the fuel we use is uranium-235. This is the mass number of the uranium atom, and well, you may see a lot of different diagrams like this one. They will split into something else, and after they have split up, they will also emit neutron that can help you to enhance the next reaction. And so let's just quickly see what happened here if I shoot a neutron from this gun towards this uranium. Explosion, right? So well, people may call it explosion. Of course, it's not. I don't really call it explosion, but it's just a reaction, nuclear reaction. And so what actually happened is, I hope you can see carefully. What I do is the neutron got absorbed by the uranium. One thing that I learned in the past when I was a student like you, and I thought what happened is the neutron collide with the uranium and kind of crush them. And this idea is totally wrong, because you can see it's not crushing them like how you use maybe a ball to smash a glass, but then it's more like these neutrons got absorbed and they gain the energy and then they will split. From here down below, you can also see the atom was in something called the potential well. So that is to say, if the atom does not actually gaining enough energy, it will be kind of hanging around in this well. So it will be quite stable. Only if it get enough energy to overcome the wall of the well, and in this case it will be the neutron itself, then it will be able to release those potential energy. And this is how we have a lot of energy released from the nuclear reactor. Here is something I always like to do. This is going to show you the chain reaction. So having only one uranium is no fun. What you can see is, once this reaction happens, you have the two daughter cell, two daughter nucleus I should say, and three neutron. And with only one uranium, you don't see any chain reaction because there's nothing you can chain with, right? So by increasing the amount, then something nice will happen. It will look like fireworks. So let's take a look here. It's amazing, isn't it? Well, you may see there's only one here leaving behind. In reality, it doesn't really matter because there are much more than that. I mean, here I've got 100, but let's say in reality, you may say you may have 1 mole of uranium. So how much is 1 mole of uranium? Because uranium is, as we say, is 235, and that actually means it is 235 gram per mole. So if you somehow have, well, something like 2 apples in your hand, then that is around 200 gram-ish. And with these amounts of uranium, you will have 1 mole, and 1 mole as in 6.02 times 10 to the power of 23 numbers of uranium. So it's much more with such a small amount in quantity of uranium. So whether or not you have 1 or 2 left, it doesn't really matter. Since this is so satisfying, I would like to see it again. So 3, 2, 1. Brilliant, isn't it? So here I would like to try another thing. We'll also try to add 238, or how about this, without adding 235. Let's take a look at what happened to 238 if we shoot a neutron to it. As you can see here, I've already done it. The 238 become 239. So 239 and 238 are both something that is not very useful in nuclear fission. And in reality, in the nature, when you find uranium, you can never find something that is as pure as what we have here, 235 for all of them. There would be a mixture of both usually because of the nature itself. These two of course are something called the isotope. They have the same number of proton but different number of neutron, and therefore they will behave differently. So if I have a mixture of both, then you may see that the reaction actually may not be as fast as you thought. And this is something that we have to overcome in reality. Here is the last step of the whole simulation here, which is about the power plant. So you may want to see that just now we start with 1 nucleus and then chain reaction, and then here is the biggest scale, which is the whole power plant. What we want you to learn here is you can see there is something called the control rod. In reality, it looks something like this, which may not be easy to see, but then it's really just some long sticks. For the detail, I would like you to find out by yourself later on, so I'm not going to tell the answer directly to you. You may want to observe and take a look first. So here what I can do is I can push a button to fire the neutron, and I'm going to do it now. 3, 2, 1. And you can see, well, sometimes it just doesn't happen at all, right? Because maybe the neutron just all collide onto the wall, and maybe we have to fire another one, and hopefully the chain reaction can actually happen. And you can see also by the color, and also this is a thermometer, something's wrong or something's not very good happen. Let's take a look again. So again, it is very satisfying to see all the reaction going onwards. You can see the energy produced and also the power output. But at the same time, put it into the practical point of view, sometimes you may find the temperature go a bit too high. And the problem with that is then the container of the power plants may be risk to melt down. And this is something that happened in some accident in the past. One of the most famous nuclear disaster or accident is called the Chernobyl in Ukraine. And well, you can see it from some pictures here. And also more importantly, there is a documentary about Chernobyl, the whole event, how it was happened, and how this affects the life of the people. Even there were some people making lies about the whole event, and therefore the people are not aware of the danger of the nuclear power plant accident. So highly recommend you to watch it if you have time. The accident was in 1986. Coming back to here, so how can we actually control the temperature to prevent melting down then? Let's take a look. When we fire the neutron, well, if we fire the neutron, what we can do is if we see the temperature go too high, we can actually use the control rod to lower the activity. Of course, in reality, it will be done by computer instead of like a man like playing some sort of mini game like me. It will be very silly. Of course, it's all controlled by computer to see whenever there's a high temperature, then they may make it higher or lower depending on the temperature output. And the whole mechanism of control rock is simply by absorbing the neutron. So just now, if you pay close attention to the details, then you can see the neutron basically is like gone in this simulation, and in reality they absorb the neutron simply. So now you understand how the nuclear reaction takes place, and the rest will be very easy if you try to think about from the energy perspective. So chemical energy was released in the nuclear reaction, just like you saw in the simulation, and now those chemical energy is in a form of thermal energy. In the orange area in this picture, those will be water carrying those thermal energy, and they will carry it to the steam generator. In the steam generator, there will be some water to absorb those thermal energy, and for enough energy, then they will turn into steam, and the steam will run through the turbine. The turbine will be driven in the form of kinetic energy, and those energy will be turned into electrical energy, just like you learned in chapter 5. So for now, I would like to give you some time to find out the definition of these 4 things. You may want to read textbook. You may also, if you like to, watch this video or even try to Google the keywords. Pause the video now and come back to me afterwards. Okay, so the first thing is called the critical mass. In your textbook, it says the critical mass is the minimum mass that is required for the reaction to take place. And if you try to search online on Google, or if you look up Wikipedia, and of course I know it is not a reliable source, but usually it will be quite useful for learning. So that's why we could still use it for learning. And it says the critical mass is the smallest amount of the material you need for sustained reaction. So here I would like to reinforce an idea so that you can put more detail in a case where if the IB exam asks you to define this term. I would like you to look up here. So basically the idea is very simple. Critical mass is not just the minimum mass, but it's the amount of the mass where there's a value called K, the multiplier factor, will equal to 1. And in that case, it will be self-sustaining. And what it means by self-sustaining is simply means there's no increase or decrease in power or temperature or the neutron population. So everything will be very peaceful. It will be just continuing forever if there's enough fuel. However, there's a chance where you may have the critical mass to be or the factor to be less than 1. So you can imagine it is just like a number you keep multiplying with 0 point something. So then your reaction rate will become less and less and less. Or the other way will be K greater than 1, and again you can imagine there's a number you keep multiplying with a number that is greater than 1. So for example, it's 1.5, then every time you kind of increase by 50%. So in that case, you can imagine for both of them, no matter it's smaller or bigger, then the reaction will go in loss control basically. So it's either going to be no reaction at all at the end, or the temperature will be going too quickly that it will destroy itself. As I said, it will be melting down the cage that you put down the fuel. So here I will put down critical mass as minimum mass for the reaction to happen, for a sustained reaction. Okay. The second thing is called the moderator. In your textbook, the moderator is described as something that slows down the neutrons, and it is achieved by the collision of the neutron with the atom of the moderator itself. So what is moderator then? It is usually made of water or the graphite, and this is a material surrounding something called the fuel rods. We'll talk about later on. Well, fuel rod actually we can talk about now. It's just nothing more like fancy than just the fuel that you use, and usually it's just the uranium itself. And so for the moderator is something to slow down the neutron. But the problem is, why do we want to slow down the neutron then? And here we have provided you a very clear idea, and this is something that I find very important. So here it said the neutron produced in the fission reaction, if it is too fast, it must be slowed down before they can initiate a further reaction. And this is something that I find extremely difficult to understand at the first place when I learned this, because wouldn't have the fastest speed of neutron can help us to make sure the reaction will happen? The answer is no. We don't want a fast neutron. We only want a slow neutron, because when you shoot the neutron to it, it needs to be captured or absorbed by the uranium nucleus. The reason is that you can think of the uranium nucleus as in a magnet, okay, and the neutron actually is attractive to the nucleus, and you can also imagine this is maybe like an iron nail or like a paper clip or something. And so what you do is simply you flow the iron nail, the neutron, to this magnet. And think about this: if you try to flow this too quickly, or imagine if this is not iron nail but a bullet, bullets of course is very quick, and if it's too quick, then of course the magnet would not be able to capture it or absorb it. Okay, so this is the idea here. So that's why we need the moderator to slow it down. Of course, in reality, it's not really magnet and iron or bullet. It is a certain force called strong force that you learned in chapter 7 or chapter 12. But the nature is basically the same here. Okay, so we have done the first three, including critical mass, moderator, and fuel rods. Fuel rods again is just the fuel, the uranium, the place where you provide the fuel for reaction to take place. And leaving us with the last thing, that is called the control rods. For control rod, actually we have already shown in the simulator, and the idea is very simple. Depending on the rate of reaction, if it is too fast, you want to lower it, then you can lower the control rod. Control rod is to absorb the neutron directly, so that basically the neutron would not be there to collide with anything else. Or if you want to increase the speed of the reaction, then you simply remove the control rod or take it away. To end this video, let's try to do this question, pause the video and check the answer later.
A few moments later.
Okay, so in this question, they told us 800 megawatts is something you produce, so it will be the useful power of the power plant, but it has a certain efficiency, and then the energy you can release from the fission one nucleus of uranium is this one. So this is more like the input, okay, but it is for one only. You have to calculate the mass of uranium you need for 1 year. So the easiest way to start with will probably using the efficiency equation, that is the useful energy or power over the total one. Okay, and so here we have 35%, so I'll write as simply 0.35, and then useful power would then be 800 mega, but you can see here this is in the unit of watts, so we want to find for 1 year, so we would be using multiplying with 365 days, 24 hours, 60 minutes and 60 seconds. So you can calculate all the energy you need to produce at the end for the whole year. Down below, it will be like the material you need to produce such an energy before calculating the efficiency. So here we have 170 mega. Notice that one thing that is very tricky is it is in EV, and it is a unit of energy. And if you remember, we learned in chapter 5, you can somehow change it to joule. If you don't remember, in chapter 5.1 part 3, I'll put the link in the description below, so you can take a look of how you can convert that again. So here we will have to multiply a number that is 1.6 times 10 to the power of negative 19 to change it to joule. But then again, this is only for one nucleus only. So we have to find out how many nucleus in total we need. So a total number, I'll use the big N to represent. So after we find out big N, there should be a way to find out the mass for sure. Using your calculator, you should be able to find out the big N as 2.650, well, let's just take it, yeah, 01 times 10 to the power of 27. So this is the total number of how many you have. So in order to find out the mass, I think the easier way to do is to find out how many mole first. So there's an equation that you learned in chapter 3. Again, if you don't remember, you can visit my video in chapter 3.2 part 1 about Avogadro constant and molar mass. So we can find the number of mole in small n symbol using n big N over Avogadro constant, and that would be the number that you find earlier divided by 6.02 times 10 to the power of 23, and you find the number of mole as in 4,402 in the unit of mole. However, after you find this is not even the end of it, because they want you to find the mass instead of mole, right? So you have to think about the fact that for uranium, it is uranium 235, it actually means that it is 235 gram per mole. So in order to find the mass, you could simply multiply the number of mole with 235, then you can get the answer of 1034507 gram, and put it in a more suitable unit, kg, then you will find it's around 1034 kg.